ठीक है। सो हेलो गाइस, आज हम देखने वाला एक क्रेजी थ्योरम के बारे में। ये थ्योरम हमें पी सिम्पसन लाइन के बारे में बताता है। तो पहले हम देखते हैं कि क्या कहता है ये थ्योरम। तो समझो कि हमने जो है एक सर्कल लिया, उसमें एक ट्रायंगल ड्रॉ किया। मतलब ये जो ट्रायंगल है ए बी सी, और ये जो सर्कल है वो सर्कल इस ट्रायंगल का सर्कम सर्कल है। तो अगर एक ट्रायंगल के सर्कम सर्कल पे पी इज अ पॉइंट ऑन द circum circle of triangle ABC, ठीक है। तो P is a point on the circle of the triangle ABC, तो ये कहीं पे भी हो सकता है। And then we draw perpendiculars from it. We say D, E and F. D, E, F are feet of perpendiculars. Feet of perpendiculars from P to BC, AB, comma, AC. Then this theorem says that D, E, F will be collinear, ठीक है। that is what it says. तो मैंने ऑलरेडी एक लाइन बना रखी है, that is DEF, to show that it is collinear. तो ऐसे ही बनेगा. Now we have to prove that that happens. So let's start, I guess. Now for this what we can do is we will copy this figure, some other things also. We won't talk about that. Yeah, we'll just copy this, duplicate it. Yeah. Now what all we don't need, that I'll remove. Yeah, DEF was not copied anyways, and then one thing we are missing, that is C. So yep, let's start now. Okay, now we have to prove that DEF is collinear. The first step that we will do, so wait, I'll write all of these steps here. Step 1, join F and E and D and E. So now what we will do is we will just join this and then we'll join this. So now we don't know that DEF is a straight line. We have to prove so. But we know that AB is a straight line. So the RTP for us is required to prove is that DEF is collinear, which we can prove by saying that one angle on this point is 180 degrees, that is DEF is 180 degrees, which we can do that. But there is a slight variation that we can use, which is if we prove that these two angles are equal. Which two angles? These two angles, if we prove that they are equal, then we will also prove that DEF is a straight line. Because see, if we know that one line is a straight line and other line we are not sure about, so we can say that this angle is 180. Okay, this is some x. Then what will this much angle be? It will be 180 minus x. And if we prove that this angle is also x, this total becomes 180 again. Then this becomes 180, which also tells that this line is a straight line. So that is what we are basically going to prove. Okay. So let's start, I guess. Okay. I will join this first because something things can be seen here. And then see, this proof is based on a lot of cyclic quadrilaterals that we are going to make on the way. So I'm trying to make as much of them as I can. Okay. And what else can I say? This is there. Okay. So first we have to look at the quadrilateral FAEP. Okay. We can notice that it is a cyclic quadrilateral because we can see that the opposite angles are supplementary. This angle is 90 degrees, this angle is 90 degrees. So the opposite angles are supplementary and hence it is a cyclic quadrilateral. By which we can also say that a circle passes through it. A circle passes through this quadrilateral. Okay. And then if we look carefully, we can see that this is a chord on a circle. And then this is a line like this. This is also a line. Okay. Yep. These are two triangles formed by the same chord on the circumference of the circle. So can we not say that this is also x? This is also x. Okay. These two angles are now officially x. Okay, I shouldn't have written it. Now I'll write it. This angle also becomes x along with this. Okay. Now that I have said, we will notice some more cyclic quadrilaterals like APBC. APBC is also cyclic quadrilateral because it lies on the circumcircle of triangle ABC, by which we can also say that angle BPA is equal to angle, no, not equal to, is supplementary to angle ACB. Like this we need to write. So if I call this angle P, what will this angle be? It will also be 180 minus P. Okay. Now we need to find one more cyclic quadrilateral. So let's just find that. We don't know that what is this angle. Okay. So and then one more cyclic quadrilateral is this one, which is PEDB, through which we can say that these two, this angle and this angle, are two angles subtended by the same chord on the circumference, by which those two become equal. So if we then we can say that DEB is equal to angle DPB. Okay. Now if we can prove that the angle DPF, not DPF, APF is equal to DPB, then we can say that we have proved what we needed to. And to do that, what we need to do is we need to get the last cyclic quadrilateral of the game, which will finish the game for once and for all. That is the quadrilateral PFCD. It is also cyclic quadrilateral because if you look carefully, this angle is 90 degrees. Okay, wait, I'll get a nicer color, better color. This angle is 90 degrees. This angle is 90 degrees. And these two are opposite angles. So opposite angles are supplementary. And hence, these two angles are equal. Now what can I say? Now I can say that this angle will be supplementary to this angle. Okay. So I can say that the angle DCA will be equal to angle DPS. Okay. DPS, which is also equal to, see here we have said that. Why am I writing equal to? Wait. So this plus angle, what is that? DPF is equal to 180. What else is equal to 180? Angle DCA plus angle DPF is equal to angle ACB plus angle BPA. Okay. And by this we can see that angle ACB is the same as angle DCA. Okay. So these two angles are same, so we cancel them out. We can say that angle DPF is equal to angle BPA. Okay. So now I can also say that this is P as well. Okay. Now see what case we have. I'll bring it out here. So there is one thing like this. There is one line that goes here. There is one more line that goes here. Okay. And then there is one line that goes like this. And we know that this angle is P. This angle is P. Okay. So can we say that, see, this is B, this is P, and this is D, DPF, and then this is A. Okay. So can I say that angle BPA is equal to angle BPD plus angle not P, wait, plus angle APD. What is angle BPA? Angle BPA is P. So we are saying that this whole angle is equal to this angle plus this angle. Now that is correct basically. So we will write that again. Now the next will be with this one. We'll write here that angle FPD will be equal to, or rather than writing FPD, these two are equal. So I'll write BPA itself. PPA. Because see, this is also P, this is also P. I'll write that. Which is equal to angle FPA plus angle APD. So now those two are equal, so we equate these two also. We can write angle BPD plus angle APD will be equal to angle, okay, wait, angle BPD plus angle APD will be equal to angle FPA plus angle APD. Now APD is common on both the places. We remove them. We can say that angle BPD is equal to angle FPA. Well, what is angle FPA equals to? X. Then BPD will be equal to X, which means we have basically proven what we needed to see. This angle, rather with the highlighter, this angle is X. So then this angle will also become X, which is equal to this angle, as we have said in one of the things. And this is also X, one of the statements. See here, DEB equals DPB. So now we have proven that the line is collinear, and this line is known as the P-Simpson line. P, not Simpson, P-Simpson line. Okay. So, and now why is it called P-Simpson line? Because the line is drawn because of the perpendicular. The line is drawn through the feet of perpendiculars drawn from point P. So it changes on the basis of the name of the point. So if the name of that point is Z, it will be Z Simpson's line, etc. Okay. And now we have not assumed the position of P. We have only said that it lies on the circumcircle, which means that it can be anywhere on the circumcircle and it will work. So yes, this was a wonderful theorem. And finally, we have proved it.